terminal, and it has to be in the same direction with the what? Can you find point B is more challenging to acquire the first moment of area when compared to point A? That's the one. So, you're okay? Point B, where will you take? Now you see that we can take one people, right? So that's the way like what's the thing you need every so. Right. So I'll give you another. So some of us might think, Eugene, you know what? Without the rules I'm going to tell you, you might consider if I'm going to look at point B, being a mechanical engineer, we see to believe, we say, Eugene, isn't this the whole area? Yes or no? Right? Why I say that, right? Why I say that, right? Because you see how the shear flow is flowing, right? It's from point A now. Now, that's not correct. The correct area to take is this. So the one in pink, this is the correct area. Now, as I said, you don't learn this from textbooks, you learn from doing a lot of questions. What is the logic behind it? What is the logic behind it? The logic behind it is this. The area you consider has to be the close relative to the what? Nearest terminal. So number one is nearest terminal. And the shear flow direction has to be the what? Let's see. I repeat again. The first moment of area to consider which first moment of area to consider is number one, the nearest terminal. Number two, the shear flow direction is the same. When I say the same, it has to be ends. Has to be the same. Is either going to be horizontal Q or vertical Q. Are we clear? So if you look at this, right? If you look at this now, right? The closest is 1 or 2 for point B and the 2. And it has to satisfy the logic. If you look at terminal 2, the shear flow is in what orientation? Okay. Be clear. Okay. So when you do that, now you can calculate the shear flow at B. Okay, so now we can determine the shear flow at B. So over here, we now want to look at point B now. So now, because you know how to design the shear flow, over here, come on, over here is your terminal, and these are your shear flow direction. So if we look at point B, it's again going to be what? Box beam analysis. And then you're going to look at what? 2Q. Okay. And then your first moment of area will be equal to what? So the first moment of area, so this is the width is 125. The depth is 0.01. The y bar is now equal to 0.1 plus by 0.01 divided by 2. Okay. So this is equal to 0.1 plus by 0.01 divided by 2 times by 0.01 times by 0.125 is equal to 131.25 times 10 to the power minus 6 meter cube. So for this case, your shear flow Q at point B is equal to V, which is equal to what? Our V is equal to 18 times 10 to the power 3 multiplied by 131.25 times by 10 to the power minus 6 divide by your second moment of area, which is 125.166 times 10 to the power minus 6. And then you have to divide by 2 because it's what? Box beam. So this will be equal to 18 power 3 minus 6. It's equal to 9.437. 9.437 times 10 to the power of 3 Newton per meter. Are we clear? Now you see the importance of designing the what? The shear flow. Let's look at another example. And by looking at another example, you say, it is so easy now. Okay. Now, you still have to obey all the previous rules, okay? Yes. Go to where? Well, let me paste. Yes. Okay. Okay. Let's look at the next problem now. The assembly is subjected to a shear V equal to 7 kilopounds. Determine the shear flow at point A and B and the maximum shearing stress. You have to ensure that you know where the centroid is. Here. Right? Why you have to ensure that you have to know where the centroid is? So sometimes you can cover the top, you cover the bottom, then you are more sure on whether you are looking at a box beam or what, or a white flange. Okay. So look at point B now. So I'm not going to find the first moment of area, or do I need the second? Okay, I'm not going to find the second moment of area because all those are known. So I'm going to provide that we have our IZZ. Before we go on, I'm going to throw a monkey wrench. Okay, before we go on, I want you to look at this problem now. And this is our Y This is our Z, and this is our X. So we know over here, this is our point A. And we know that this is our shear flow direction. Okay, I'm just going to draw part of it. Then over here, this is our point B. If we put an element over here, okay, now we put an element over there. Okay, so this is now my element. Okay, and this transformation, I do apologize, the transformation should be relative to the element. And now this is our Y and this is our Z. We know that this is our shear flow direction, but what is it? The shear, the intersecting plane, this intersecting plane is which plane? Anyone? This plane will intersect the which axis? That plane will intersect the which axis? It's parallel to Y, it's not intersecting Y. So if I draw this plane, I draw over here, can you all see what plane is it intersecting, yes or no? So it's intersecting the X plane, and the shear flow is in which direction? Z direction. Are we clear? So that is the direction of the what? Of the shear stress that we are looking at. You have to know all this because we are going into 3D mold circle. For 3D mold circle, you need to know all the orientation. If not, are we clear? Okay, you need to know your orientation. Hey, listen. This is not difficult. You find overwhelming for now because this is the first time you are seeing it. Are we clear? It's parallel to Z. The shear force is parallel to Z, or the shear flow. Are we clear? Okay. Now let's look at this problem over here. Let me paste on the next page. Hey, diagram. Right. So the first thing we're going to do, okay, we are going to design the shear flow again. Okay, so I'm going to sketch. If you don't design the shear flow, this topic is as confusing as it what? As it comes. And if you don't design the shear flow first, you have not a clue which first moment of area to take. Not a clue at all. I don't know. How do you think about thin wall now? Is it fun? Yeah, it's like solving puzzle, isn't it? Not like dumping shit into a formula, yes or no? Right? You have to learn how to solve the puzzle first. Okay? Right. We have a shear force coming down, right? Which is your Vy is equal to 7 times 10 power 3 pound force. So when we do this, what do we design first? The shear flow, right? So what controls the direction of the shear flow? The what? Major web. Major web is coming down. The top look kind of confusing, yes or no? Right? What must it be? Right? So you know that there's a terminal